Now, let's say that you have performed different algorithms for the same problem, then it will be a good idea that you perform your algorithm with different probability values and check for the accuracy. It would be good if you draw ROC curve also, and then your client would be happy to have better visualization with respect to this ROC curve, right? So more the information which you are providing with respect to your data and the algorithm, better it is for your project. So don't stick with always 0.5. I wanted to cover this sixth session, and that's the reason after completing this sixth session, I wanted to talk about this ROC and AUC. Okay. So this will again come in the advanced course also. But then I wanted to give you about the same so that after completing even a first course, you should be having the sufficient knowledge. But yes, the more knowledge we have, we can always expect a better opportunity. Okay, so now we have come up with a new classifier which is called as support vector machine. Again, support vector machine, I'll be going through with the classification. You should tell me in the next session whether the support vector machines can be used for regression or not. The reason I always train for classification because there are a lot of projects out there for classification. Now, apart from the other methods what we have looked for classification, there is also one more method which is called as support vector machine, which is SVM. As I already told, support vector machine is also used for regression, but it is widely used for classification projects. Let's say that you have two input features. Let's say that you have two input features which are x1 and x2, which are shown here. And your output has two classes. Those are represented by 1 or zeros, or ones are represented say by square and zeros are represented by circles. So if you remember in the previous session also, I have explained you underfitting and overfitting with the help of this graph, right? By drawing two different classes, something like that. So now, what do you think what I am doing here with different lines? I'm just trying to segregate the classes, right? For example, for this class, for example, this line which is segregating these two classes tells that if x1 is less than this point, if x1 is less than this point, I'm just trying to give you one example, okay? So don't consider in that way, but the whole point what I'm trying to explain here is there are different lines which can separate these two classes, right? There can be infinite number of lines which we can separate these two classes. But why are we trying to separate out these two classes? If we can separate out these two classes, then it will be easy to understand what kind of input features belongs to this class, what kind of input feature belongs to this class, right? Simple. So to understand that, we are using support vector machines. The reason why people generally go with support vector machines, it's because it's quite simple and it provides good accuracy also with less computational power. So that's the reason people generally go and use this support vector machines. Now, if we have infinite number of lines, if we have infinite number of lines here, which can segregate the two classes, then which could be the one which we should use, guys? What do you think we should use? I can have infinite number of lines here. This is one more line which is separating this out. The line which separates out the two classes with a sufficient tolerance. Sufficient tolerance in the sense, let's say if there are lines here, the line will look for a nearest points and then it will consider, it will always take a line which has the maximum margin. So now we have a sufficient amount of freedom telling that if there is a new point which comes in, for example, if I am getting a new point here, then we can tell that it belongs to class square, right? So there is a sufficient amount of bandwidth, and that is where margin is helping us. Maximum margin will help us in identifying an optimal line which separates out these two classes. And this optimal line is called as hyperplane. Now you must be thinking, why is this line called as plane? Okay, so this is the only example which we are considering in 2D. Imagine we have three-dimensional. Again, we have two different classes. So in 3D, let's say you have three input features x1, x2 and x3, and you have two different classes in your output y which are 1 and 0, and if you want to segregate that out, then you have to segregate that with the help of plane, right? So that's the reason we call it as hyperplane. Okay, now let's say I had one more class here. Let's say in my output I have 3 different classes. Then how will you differentiate this? How will you come up with the hyperplanes? So you have to come up with the answer for this in the next session. Okay guys, so let's go back to our previous example when you have 2 classes. Okay, so think on this. Okay, I don't want to tell the answer now. So in 2D it's okay, it's a line, but in 3D it's a plane. Okay, that's the reason it is the common name has been provided with hyperplane. Okay, now the nearest point, for example, for this line, let's say these are the nearest most points from this class, and from this class this is the one. So these are called support vectors. Why is it called support vectors? Because from this we calculate the distance margin, which is called as margin in support vector machine language, and this distance has to be maximized, right? So that's the reason the name coming in support vector machines, because this point very near to the line are called as support vectors. So I have again 2 features and I have say 2 classes. Okay, now I have different lines, say 1, say 2, say 3, say 4, say 5. Now tell me which would be your optimal hyperplane in this case. I have given the numberings. I have 2 features, x1 and x2. I have 2 classes. Right, 4, right? Because it has maximum margin. Right? Great. So now let's quickly go with some more examples so that you can understand support vector machines in a better way. I'm just giving you some different examples, guys. Okay. Let's call this as 1, this as 2, this as 3. So out of 1, 2 and 3, what do you think which could be depending on distance? By looking at the graph, what do you think? Which one is better? Which would have the maximum margins? 1, 2 or 3? 1, 2 and 3. Which is better? Which has the maximum distance? 3, right? So if you notice, 3 would be having the maximum distance, right? But let's say that you have this kind of, let's say, you have 2 different features, x1 and x2, and these are your classes. Now how to segregate this using hyperplane? Right, so you're right. So this should be the hyperplane, right? If you look into this, by looking at this graph, it's clear that this should be the hyperplane. But then how does support vector machine does it? It would be very difficult for the support vector machines to generate this kind of hyperplanes, right? Okay, I think today we have got a good amount of knowledge about ROC and AUC because that is very important. So support vectors are the ones which are here, okay? These are the support vectors, okay? The ones from which we are calculating the margins. Those are called as support vectors. With the help of support vectors only we are able to come up with the hyperplanes. And support vector machine, it's just an algorithm name because we know what is support vectors. So that's how the name has come in, support vector machines, which is an algorithm. It's an algorithm name like random forest or decision tree. Okay, so I just recollected that I haven't given the puzzle after first week. As I told, in data science, logical thinking is very important. Okay, so from next time, please keep reminding me. Okay, now let's say that you have 10 jars. Okay, so there are 10 jars, and then each jar has 50 toffees. Toffees in the sense candies. Okay, each jar has 50 toffees, and let's say that each toffee weight is 10 grams, each candy. Okay, so each jar weight would be 500 grams, right? Apart from the jar, just if I'm just calculating the weight of the toffees, then it would be 500 grams. So now out of these 10 jars, there is one defective jar which has all the toffees or candies of only 9 grams. Okay, that means the total chocolate weight would be 450 grams. Now you have to identify this defective jar. You have a digital balance. You know digital balance, right? Nowadays people are not using common balance. They are using digital balance for weighing some components, right? Now fruit shop, vegetable shop, everyone uses digital balance, right? It will show you the weight here. You can use this digital balance only one time. That means whatever you want to keep on this digital balance, you can keep. But once the value is shown here, with that value only, you should be able to tell me which is the defective jar. You should tell me that strategy, which is the defective jar. You must be thinking that I'll keep this jar first and then I'll keep this jar. It's not a case. You can use digital balance only once. Once you got this value, once you are visualizing this value over this digital balance, that's it. You cannot use it furthermore. So you have to tell me what could be the strategy that using digital balance only once, we would be able to identify this defective jar. Okay? Did you understand the puzzle, guys? Cool. Great then. So please work on this and I will ask you the answer tomorrow. And please keep reminding me, guys. I want some fun also in the sessions and this will improve your logical thinking. Okay, now this is the example which I was talking about. So you have this kind of classes. Now it's very difficult to classify this, right? But if you try to look it in these directions, let's say this is your x1 and this is your x2. Okay, now let me correct this. So let's say this is x1 square and this is x2 square. So if I come up with an equation z square equal to x1 square plus x2 square, then don't you think I'll be getting the z value something like this? Because the ones which are very near to origin, the value will be lesser, will still remain near to the origin. The stars which are away from the origin will be slightly away from the origin. Now it will be easy to classify this using hyperplane, right? Now using this, it will be easy to find the linear hyperplane for this, right? But then you must be thinking it would be really difficult. We have to do this, we have to come up with this z square manually while doing the project. No, it's not the case, guys. Fortunately, there is something called as kernel tricks. Inside support vector machines, there is something called as kernel, a kernel trick, which transform the data in a way that the classes can be separated out by linear hyperplane. Okay, so this is the inbuilt feature of support vector machines. Okay, and there are different kernels which are inbuilt in support vector machines which you can read over Google, but then there are different kernel tricks, but then this is the one which I'm talking about, the transformation. What does kernel trick, what does kernel do? That is more important. People will not ask you what are the different types of kernels. How does kernel helps in our analysis? Kernel is transforms the data so that it could be easily classified using hyperplane. That's called as kernel trick. And then there are different kernel methods which you can use in Python. Now I'm telling about this different different kernels, right? What are these called as? Say the probability value in logistic regression as a threshold value, right? Do you remember the probability value which you are changing? So what are these called as? Note down, guys. These are called as hyperparameters. So every algorithm will have different hyperparameter, and that hyperparameter will decide how fast your algorithm is in terms of computational time and how much accuracy you are getting in. Okay, so because say with different threshold values of probability you might have different results, right? Similarly, there are different kernels in support vector machines. You might have to choose different kernels and check which kernel is giving us a better accuracy. So kernel is our hyperparameter in support vector machine. Similarly, probability was a hyperparameter for logistic regression, probability value, right? So now, can you recollect what could be the hyperparameter for linear regression? See, I'll be talking about different things while discussing different algorithms whenever it is required. So we might have to go front and back, okay? For linear regression, what could be our hyperparameters? Slope. How can slope be an hyperparameter? We are not deciding the slope, right? We are not changing the slope. Slope is the one which would be our output. Beta naught and beta 1. We are getting those beta naught and beta 1 as an optimized value using gradient descent method, right? What we are changing, what values we can change by which our output could be affected or our computational time could be affected. If you remember, in the gradient descent method, I have talked about derivatives, right? Tangents. So when we have taken the tangents, I told you we cannot jump from this point to this point directly. We have to go slowly so that we do not miss our global minimum point, right? So for that, what we have done, we have chosen a learning rate, right? And then we have to choose the learning rate sufficiently small, right? So learning rate was our hyperparameter in linear regression. In logistic regression, you can consider the probability values. Can you tell me what could be the hyperparameter for random forest? See, now you know hyperparameters for linear regression, support vector machines, and then logistic regression. Can you tell for random forest, guys? It's simple, no? Number of trees. If you remember, by increasing the number of trees, the accuracy will increase, and then at one point of time, if you even increase the number of trees, the accuracy will decrease, right? So this is your hyperparameter for random forest. Okay, guys? So similarly, you will notice for support vector machines, there are different hyperparameters. Apart from kernels, there is something called as gamma also. So now this is your homework. You should tell me tomorrow what is the significance of gamma in the next session. And I have given the data section, and then for different weeks they have provided them the different data sets. So they will be providing you the data set, and then you have to implement support vector machines on that, and then you have to come up with a confusion matrix. Okay, so you have to tell me what are the pros and cons of support vector machines, and then you have to tell me the significance of gamma. Okay, so, and guys, now it's high time that you should start working on your assignments. You don't worry about overfitting and underfitting now. You can just tell me what you can do whenever you are trying to implement any algorithm to any data set. Just apply it in Python. First, you have to do a lot of exploratory data analysis. Before that, you have to import the CSV file using pandas. Second step, do a lot of exploratory data analysis. Third step, split into training and test data set with 70-30, with different things you can use. 80-20 you can do, it's up to you. 90-10, and can check whether which split of the data works better, and then train your model with different algorithm, then test it, and then find the accuracy using confusion matrix. Okay, and then you can tell me whether it is overfitting or underfitting, and if it is overfitting, what all things we can try. If it is underfitting, then what all things we can try. Okay, in general, in the initial phase, this would be sufficient if you can perform the algorithms and tell whether it is overfitting or underfitting. For each algorithm, there are different ways tackling overfitting and underfitting, and there are some common ways also which you can look for. But in general, the generalized methods, what we can do, you can try these things also anyways, this ratio percentage values, or you can use transformations such as z values. If you remember, do you remember z values? X minus mu by sigma. Convert all your features in z values, and then you can check. So you can do this also. You can use different hyperparameters. That could be one more example. Use different hyperparameters. But then in general, what we do is, which you will be learning again. So in general, for underfitting, what we do, if the model is going through with underfitting, then what we do, we try to complicate our data. What do I mean by complicating? We try to increase the number of input features. We try to identify if there are any more features, because the features which we already have are not sufficient for predicting our output. So we have to come up with additional input features. This is one of the ways. For overfitting, what you can do is you can increase the training data set, or you can use some regularization techniques that we'll be learning again in the advanced course, but you can use some regularization techniques. But apart from this also, if you can look into these different techniques what I've taught, splitting of data, hyperparameters, z values, we should be able to come up with the optimum results. If the model is underfitted or overfitted, then we have to use different techniques for that. Okay, great. So